So we know that if we increase the temperature of something, the particles are moving faster and they have more energy. So they're going to collide more often. Remember, if they collide with proper orientation with enough energy, they are more likely to have a successful reaction, right, than just a normal collision. Most collisions are not successful. Proper orientation with enough energy, we can get a successful collision. If we have more particles, if we increase concentration of reactants, then we also get more collisions. If we increase the surface area, for example, we grind up something that where the center particles are not exposed. If we expose those particles, then we can get more collisions. Catalyst. A catalyst, remember, you need to collide with proper orientation and enough energy. The catalyst lowers that energy requirement. That energy requirement is called the activation energy. So if we lower the activation energy, we are going to have a more possibility of a successful collision because we now have a lower energy requirement. The way the catalyst works is the catalyst basically finds a new pathway, finds a different way for the reaction to form the activated complex. Cool. Let's open to page 3 and check out these energy diagrams first today. These energy diagrams help us see how reaction progression goes. So if we take a look, on this side right here, we have the reactants. On this side right here, we have the products. Now, this is the potential energy of the products. And this is the potential energy of the reactants. So this is energy that's normally in kilojoules. This is the progress of the reaction. This right here is a transition state. You will hear me call this the activated complex or something like that. It's an intermediate state between reactants and products. The activation energy, if our reactants have this much energy, they have to have or gain or get somehow that much energy, that many kilojoules of energy to get to form that possible successful collision with the activated complex. If we use a catalyst, this is lowered because of an alternate pathway. If we raise the temperature, well, that's going to raise this initial energy, the potential energy of the reactants. So that may get them closer to that energy of activation. They can get that. So here we have a diagram with some numbers and some letters identifying certain areas. So let's take a look. The activation energy for the forward uncatalyzed reaction. So if we take a look here, we need to find something that goes all the way up to there, or we can count. We're at 5, so 1, 2, 3, 4, 5, 6, 7, 8 kilojoules is one way we can look at that energy. Or I could just give this line a letter, like I can just call this, let's call it K. So that activation energy is K. What's the activation energy of the forward catalyzed reaction? A catalyzed reaction a lot of times is shown by writing a dotted line underneath. So if we go, that's 1, 2, 3, 4, 5, 5.8 kilojoules. Or they already have a letter that I don't have to put one, they have the letter F. Delta H for the catalyzed reaction is, let's take a look. Remember delta H from last semester? That is a change in energy overall in the system. So if we take a look, this is how much energy the reactants have. Do the products have more or less energy? More. So that right there tells us this is endothermic. So this reaction is gaining energy. It is what we call endothermic. How much does it gain? 1, 2, 3. So 3 kilojoules, or just H. How about for the uncatalyzed reaction? Well, take a look. The amount of energy the reactants have and the amount of energy the products have, it does not change. So it will be the same. The activation energy for the reverse catalyzed reaction. This is something we're not going to talk very much about. A reverse reaction, if reactants go to products, some reactions are reversible. For example, we know that we can separate water into hydrogen and oxygen through electrolysis. We also know that if we react hydrogen and oxygen together, we get water. That's a reversible reaction. Problem is, electrolysis, you've got to put a lot of energy back into it. Takes a lot of energy, so the activation energy may be high to get it from H2O back to oxygen and water. This one, not so much, because this is endothermic. If we want for the catalyzed reaction, all we got to do is 1, 2, 2.8 or D kilojoules. Activated complex. Let's define this as a transitional state. From reactants to products. It only lasts a small amount of time. It only lasts a very small amount of time. What is the value on kilojoules of delta H? Well, I've already answered that up above. It's 3 kilojoules. How does a catalyst increase the reaction rate? It lowers the energy required. Which we call the activation energy, by finding a new pathway. There we go. My pen's dying. Try this pen for a bit. Cool. So if we take a look, go to page 6 and 7. Similar questions there. 7's kind of neat because for 7, they want you to actually draw the line. So let's draw one. Plot the energy diagram with the following values. Potential energy of the reactants is 350, 100, 200, 300, 350. So there's my reactants. Says the activation energy needed to form is 100. So 350 plus 100 is 450. So there's my activated complex. Potential energy of products is 250, 100, 250. So this is where I want to end. So now all I've got to do is make a curve that follows that. All right, if I wanted, I could make it a little flatter right there, but no need. Is it endothermic or exothermic? Do the products have more energy or less energy than the reactants? It's exothermic. They've lost energy. It's exo. What is the value of delta H? 1, 2. So it's negative 100 because it's lost. What is the potential energy of the activated complex? 450. kilojoules. That's how we do that. So you'll draw these two for tomorrow as well and do these two. There's 4 problems. Last thing we want to do today is calculate rates. This is pretty simple as well. So if we take a look, how much, you say you work at the JECC, the Jewish First Baptist. So if you don't mind, you can make up a number if you don't want to tell me. How much do you make an hour? $10 per hour. So he currently has 0, and I don't know if this is true or not, but let's say you have 0 money in your pocket, right? You start work at 4 and you go till 5. How many hours have changed? 1 hour has changed, and every 1 hour you get how much? 10. You went from 0 to 10, so you got $10 per hour. Let's say that we go from 5 to 7. How many hours difference is that? 2, and you've found that you have $20. So we still divide that. That still gives us 10 per hour, right? That's a rate. That's how you find a rate. You have a change in something over a change in time. In the case of your money, it's a change in the amount of money you get over the change in time. We know that delta symbol stands for change. This is new probably, but these brackets right here, that stands for molarity. So that's a concentration. So out of this, what's the product? SO2, Cl2, or SO2, Cl2? What is the product here? The product. Which side of the reaction is the product on? What's being produced in this reaction? SO2, Cl2 is being produced. That's the product. How would we show that that is a concentration? We have to put what around it? We have to put brackets around it. How do we show it's a change in concentration? We've got to put a triangle in front of it. So that is a change in concentration of the product. If we want to find the rate, then we take the change in concentration of the product divided by the change in time. That will give us the rate. So the change in time is from 0 to 10 seconds. How much time passed if we were at 0 seconds and now we're at 10 seconds? Isn't rocket scientist yet, guys? How much time passed? 10 seconds. We take 10 minus 0. That equals 10 seconds. Originally, we had 0 molarity, but then after 10 seconds, we had 0.246 molarity. So what was the change in molarity over those 10 seconds?
0.246.
Yeah, right? 0.246 molarity divided by, this pen is done, so it looks like, look at that, still has all that ink in there. You would think it would be okay. They're robbing me of ink. 2.4 divided by 10. 2.4 divided by 10 is 0.0246 molarity per second. So let's do number 2. We went from 10 seconds to 20 seconds. So how much time went by? 10 seconds. Right? And at 20 seconds, we had 0.355 molar. Whenever at 10 seconds, all we had was 0.246 molar. So how are we going to find the change there? What do? We take 0.355 minus 0.246. 0.109. None of these pens work. Oh, junk. So there's our change in molarity divided by our change in time. It gives us 0.0109 molarity per second. Well, what's the time change in number 3? Right? 10 seconds. We're going to go from 0.355 up to 0.404. .404 minus 0.355. We get 0.049. We divide that by 10. We get 0.00490 molar per second. We're going to do that for all this data, and then we're going to analyze that data tomorrow before we go over the review. So you have page 5 to do, and 6 and 7. Because I divided by 10. What's the question at home?